In the thyroid gland, two forms of thyroid hormone are produced: thyroxine, which contains 4 iodines, and triiodothyronine, which contains 3. Thyroxine is the most prominent thyroid hormone that is produced. The thyroid gland produces about 80% thyroxine and about 20% triiodothyronine, T3. However, what we see is that T3 has a much higher affinity for the thyroid hormone receptor than does T4, and therefore is the most biologically relevant form of thyroid hormone. What we notice is this, that deiodinases, enzymes that remove one iodine, convert T4 to T3 within target cells. And so this means that T4, the circulating T4 in the plasma, serves as a reservoir for thyroid hormone. And it enables the body to more easily maintain constant levels of this very important hormone. What we notice is that in the synthesis of thyroid hormone, a couple things we want to make note of. One is that here we have the thyroid gland, if you follow the cursor, straddling the trachea with a lobe on either side of the trachea. If we look at the cells or the structure of the thyroid gland underneath the scope, we see these regions referred to as follicles. The follicles surround this protein-rich liquid referred to as colloid. And interestingly, the follicular endothelial cells that we see here are responsible for the synthesis of thyroid hormone. At this point, we're going to omit a small amount of material. That is the material that relates to the steps in the synthesis of thyroid hormone. And so this includes figure 11.21 and the text associated with it that's found there on page 340. In 11-10, we talk a bit about thyroid function and how thyroid hormone is controlled. This is actually a review from our previous discussions of the various pituitary and hypothalamic hormones. And actually, we used thyroid hormone as our example back in those cases. So, to review though, what we notice is this. It all begins with the hypothalamus, which secretes thyroid-releasing hormone. Plasma levels of thyroid-releasing hormone go up, as we see illustrated here. That causes secretion of thyroid-stimulating hormone from the anterior pituitary. Plasma levels of thyroid-stimulating hormone go up. Those make their way to the thyroid gland, causing the release of primarily T4, but also T3. Plasma concentrations of thyroid hormone go up. T4 is converted to T3 within the cells, and the cells respond to those increased concentrations of T3. We have negative feedback that occurs primarily at the anterior pituitary, but also to some extent at the hypothalamus as a result of the exposure of those two glands to both T3 and T4. As we mentioned previously, hypertrophy of the thyroid gland can occur. The most common cause of hypertrophy of the thyroid gland, which is referred to as a goiter, is overstimulation of the thyroid gland by thyroid-stimulating hormone because, as you know from our previous discussions, thyroid-stimulating hormone is both a tropic hormone, causing the stimulation of thyroid hormone by the thyroid gland, and a trophic hormone, which means that it controls the size of the thyroid gland. In fact, those follicular cells, endothelial follicular cells, respond in a very pronounced fashion to thyroid-stimulating hormone, both increasing protein synthesis and increasing the production of thyroid hormone. And so the overall size of the thyroid gland does increase in response to thyroid-stimulating hormone. The most common reason for this, although not the only reason, is a dietary deficiency of iodine. And so this occurs in certain parts of the world. We'll mention one example here on the next slide. And unfortunately, in that case, the body has to have iodine to produce thyroid hormone. There's nothing wrong with the thyroid gland, but it simply doesn't have the iodine that it needs to produce thyroid hormone. So it's continually bombarded by thyroid-stimulating hormone from the anterior pituitary, and the thyroid gland, even though it can't produce its hormone, it grows in size in response to that continual bombardment by thyroid-stimulating hormone. What we notice is that thyroid hormone is an exceptionally important hormone. Most cells of the body possess thyroid hormone receptors, and perhaps the most significant impact of thyroid hormone is maintenance of metabolism. We see this in thyroid hormone disorders, as we'll talk about next. And so thyroid hormone stimulates carbohydrate absorption from the small intestine. It allows fatty acids to be released from the adipocytes, and this energy is used to stimulate. It's used among other things, I suppose, but largely it's used to stimulate sodium-potassium ATPase activity. Interestingly, T3 itself encourages, it speeds up the activity of sodium-potassium ATPases. And that largely, the majority of ATP that's used in the body in any given day is used to support those sodium-potassium ATPases. And so this means that thyroid hormone is largely responsible for maintaining body temperature through the stimulation of these sodium-potassium ATPases, which is the biggest expenditure of energy that your body, one expenditure of energy that your body undergoes. We also notice that thyroid hormone has permissive actions, and the permissive actions, as we've actually mentioned before, are the most notable ones, at least, are related to epinephrine. And so what we see is that in hyperthyroidism, when you have high levels of thyroid hormone, you have upregulation of epinephrine receptors. And so even if epinephrine levels are completely normal, you have an abnormal response to epinephrine, which is very similar or perhaps indistinguishable from the response that you would see if you had inappropriately high levels of epinephrine. Lastly, thyroid hormone is exceptionally important in growth and development. Number one, T3 is required for production of growth hormone from the anterior pituitary. And so, in the absence of thyroid hormone, overall growth of the human body is greatly reduced. Secondly, and maybe even more importantly, what we see is that thyroid hormone is extremely important in the development of the nervous system. In fact, if thyroid hormone levels are low, a condition referred to as congenital hypothyroidism that leads to mental retardation results. And so this is a result of an iodine deficiency in the mother, and of course the fetus has no way of obtaining iodine apart from the mother. It's disturbing to think about, perhaps, but in parts of the world where iodine is not common in the environment and therefore in the food, iodine deficiencies historically are extremely common. Now, Chimbazar that we see in this little diagram here is a very small village that's near base camp near Mount Everest, and historically has had an extremely tough time with iodine deficiencies and thyroid problems that result from that. Very high levels of both congenital hyperthyroidism and goiters in people that reside in this area. Those have largely been alleviated now as the result, very recently, as the result of the availability of iodinized salt. In any country in the world where iodinized salt is available, then of course thyroid issues as a result of iodine deficiencies are not a problem whatsoever. It's unfortunate that some areas of the world are so remote and so difficult to access and perhaps so poverty-stricken that iodinized salt is not available in those areas, and they continue to suffer from thyroid issues only because of this nutritional deficiency, a lack of iodine. Thyroid hormone disorders have very severe consequences for human physiology, given the broad-reaching nature of thyroid hormone's impacts on human physiology overall. What we see is this, that hypothyroidism, of course, refers to low levels of T3 and T4, not to low levels of TRH or TSH, and there's one of two causes for hypothyroidism. One possibility is damage to thyroid tissue, typically as the result of an autoimmune response, or iodine deficiency, which, as we mentioned previously, are common in parts of the world that do not have access to iodinized salt. And it's important to remember, as we've talked about previously, that a goiter often results from hypothyroidism. And this may initially perhaps seem strange because you have a very enlarged gland as a result of the lower levels of the hormone that it produces. But of course, that's because of the increased stimulation of thyroid stimulating hormone, as we have talked about previously. In the United States, then, being a developed country with access to iodinized salt, the most common cause of hypothyroidism is autoimmune disorders. And so autoimmune disorders that impact the thyroid gland are referred to as autoimmune thyroiditis. And so this term refers to a collection of disorders in which the thyroid gland is attacked and destroyed inappropriately, of course, by the immune system of that individual. Hashimoto's disease is an example of such a disorder that's relatively common in developed countries such as the United States. And these disorders, of course, result in goiters following the mechanism that we just discussed. The low levels of thyroid hormone themselves, apart from the development of a goiter, have particular signs and symptoms. And so we talked previously about the role that thyroid hormone plays in promoting overall metabolism in the body. And so when you have low levels of thyroid hormone, you no longer have the stimulation of these sodium potassium ATPases. Overall metabolism slows down. As a result of that, you have increased sensitivity to cold because, as we pointed out previously, this stimulation of sodium potassium ATPases helps the body maintain a constant temperature. You also have weight gain, as you would expect, as a result of the lowered levels of thyroid hormone and the lack of stimulation of these enzymes, sodium potassium ATPases, which, as we mentioned, are the primary the largest single factor consuming ATP in the human body. Myxedema is another consequence of hypothyroidism. This occurs when molecules referred to as glycosaminoglycans accumulate in the interstitial spaces of the body, and as a result of osmosis, you have this swelling that occurs as a result of that, and this puffiness, so-called puffiness, that is evident in the face and other areas of the body. Under normal conditions, thyroid hormone prevents the overexpression of these glycosaminoglycans by connective tissue cells. But in the absence of thyroid hormone, these molecules are produced at a higher level, and as a result, you have this associated swelling. Hyperthyroidism, of course, refers to high levels of T3 and T4 that are higher than normal. And the most common cause of these is some sort of autoimmune disorder, such as Graves' disease. In the case of Graves' disease, it's worth noting here that this is an autoimmune disorder that causes hyperthyroidism as opposed to hypothyroidism. Because in the case of Graves' disease, you're producing antibodies, just like you are in the case of Hashimoto's disease. But in this case, the antibodies, interestingly, they don't attack the thyroid gland tissue, but rather they bind to thyroid stimulating hormone receptors that are found on the thyroid gland. They activate those receptors and therefore bring about production of thyroid hormone, T3 and T4, inappropriately, and so elevate the levels of T3 and T4 in the body. The symptoms are exactly what you would expect based on the description of symptoms that we gave for hypothyroidism. So in this case, instead of weight gain, you have weight loss, you have increased appetite, you have increased heart rate as a result of the permissive effects of thyroid hormone on epinephrine, and you have a heat intolerance, as you certainly would imagine based on the description that we gave for hypothyroidism previously. It's tempting to think about cortisol exclusively as a stress hormone because, of course, it is released in response to many stressors. But it's important to remember that cortisol is a hormone that's absolutely essential for life, and it has a number of functions under non-stress conditions. Before we talk about those, we want to briefly review the mechanism that lead to cortisol release. So to do that, we look over here at the right-hand side of our screen, and we remind ourselves that the release of cortisol originates with the secretion of corticotropic releasing hormone by the hypothalamus. That travels via the portal system to the anterior pituitary, causing the release of adrenocorticotropic hormone. Adrenocorticotropic hormone, of course, then circulates systemically in the plasma throughout the body, making its way to the adrenal cortex and causing an increase in the release of cortisol. Plasma cortisol goes up, And the target cells respond to cortisol. There are many, many, many cells in the body that do respond to cortisol, as we'll talk about now and over the next couple of slides. One thing that cortisol does under non-stress conditions is that it has a permissive effect, as you know, on epinephrine receptors, and this profoundly impacts smooth muscle, maintaining contraction of smooth muscle during non-stress conditions, and therefore maintaining blood pressure. Additionally, we see that cortisol is, of course, known as a glucocorticoid and is well known for its regulation of glucose concentrations under stress conditions, but cortisol is always produced at low levels, and these low levels of cortisol assist in regulating blood glucose levels under simply normal conditions. Cortisol has a profound impact on the immune system, having both anti-inflammatory and anti-immune responses. The mechanisms for this are numerous, but we tend to think about the effects of cortisol on the immune system either in terms of giving a synthetic cortisol to suppress an inflammatory response, or perhaps the increased susceptibility to illness that's observed following long-term exposure to stress in an individual. So it's important to keep in mind, though, that beyond these two commonly observed occurrences, cortisol is released at low levels constantly, and this low level of cortisol is necessary to essentially keep the immune system in check. Cortisol inhibits leukotrienes and prostaglandins. It stabilizes lysosomal membranes, preventing the release of their enzymes, and it even reduces capillary permeability in injured areas, reducing swelling associated with increased capillary permeability. And so without cortisol, all of these things are increased, and so we have this increased inappropriate response of the immune system to even small perturbations in the body. For instance, one thing that we notice is that in the case of cortisol disorders, in which there are constantly low levels of cortisol in the body, these people are much more susceptible to autoimmune disorders. Cortisol also plays a role in development. It plays a role in development of the nervous system, and perhaps most prominently, it plays a role in the development of the lungs. One thing it does in the development of the lungs is cause the production of surfactant, or promote the production of surfactant. Surfactant, of course, reduces surface tension and is absolutely necessary for the survival of the infant. One thing we notice in the case of premature births is that cortisol is given if it's very likely that a birth will be premature, to promote the development of surfactant in those lungs. Eventually, of course, as we'll talk about in the respiratory system chapter, artificial surfactant or surfactant from another animal is provided, which allows survival of that organism. But cortisol is responsible for the normal production of surfactant in the infant's lungs.